NASA missions to probe exoplanets, galaxies, and cosmic inflation. From exoplanet atmospheres to the dynamics of galaxies to the stretch marks left by the Big Bang, the three finalists in a $250 million astrophysics mission competition would tackle questions spanning all of space and time. Announced last week by NASA, the three missions, whittled down from 9 proposals, will receive $2 million each to develop a more detailed concept over the coming 9 months, before NASA selects one in 2019 to be the next mid-sized Explorer. A launch would come after 2022. Explorer missions aim to answer pressing scientific questions more cheaply and quickly than NASA multi-billion-dollar flagships, such as the Hubble and James Webb Space Telescopes, which can take decades to design and build. The missions are led by scientists, either from a NASA center or a university, and NASA has launched more than 90 of them since the 1950s. Some explorers have had a big scientific impact, including the Wilkinson Microwave Anisotropy Probe, which last decade mapped irregularities in the cosmic microwave background, an echo of the universe as it was 380,000 years after the Big Bang, and SWIFT, which is helping unravel the mystery of gamma-ray bursts that come from the supernova collapse of massive stars. One finalist, the Spectro-Photometer for the History of the Universe, Epoch of Ionization, and ICE's Explorer, will map galaxies across a large volume of the universe to find out what drove inflation, a pulse of impossibly fast expansion just after the Big Bang. The physics behind inflation is unclear, says principal investigator Jamie Bock of the California Institute of Technology in Pasadena, and it happened at energy scales too high for Earth-bound particle accelerators to investigate. The prevailing theory is that a short-lived quantum field, mediated by a hypothetical particle called an inflaton, pushed the universe's rapid growth. But rival theories hold that multiple fields were involved. Those fields would have interfered with each other, leaving irregularities in the distribution of matter across the universe that would differ statistically from the distribution expected in conventional inflation. By mapping hundreds of millions of galaxies across a huge volume of space, SFX should be 10 times more sensitive to this cosmic lumpiness than the best maps of the CMB, perhaps sensitive enough to distinguish between the two inflation scenarios. The All-Sky Infrared Survey should also map out the history of light production by galaxies, and closer to home the distribution of ices in embryonic planetary systems. SFX is more powerful than the sum of its parts, Bock says. The Arcus mission will also study distant galaxies but in X-rays, in search of what makes galaxies themselves tick. Powerful radiation from supermassive black holes at the center of most large galaxies creates winds that can blow gas out of the galaxies, halting star formation. But astronomers are unsure whether the gas falls back in to restart star formation because they cannot see it. This expelled matter has got to be out there somewhere, says principal investigator Randall Smith of the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts. He says Arcus will be able to see the winds by using more distant X-ray sources as backlights. The project draws heavily from a past mission that never flew. The International X-ray Observatory. When NASA withdrew from that project in 2012, U.S. researchers continued to develop the optics required to focus X-rays, which simply pass through flat mirrors. Based on sophisticated metal honeycombs that focus the high-energy photons by deflecting them at shallow angles, Arcus's optics should turn as many as 40% of the incoming photons into a usable spectrum, up from 5% in NASA's current flagship Chandra X-ray Observatory. That should give the mission the resolution to see the expelled gas and measure its movement and temperature. The third contender, the Fast Infrared Exoplanet Spectroscopy Survey Explorer, aims to probe the origins and makeup of the atmospheres around exoplanets. The probe will gather light shining through a planet's atmosphere as it passes in front of its star, as well as light reflected off its dayside surface, just before it passes behind. This will reveal both the signatures of atmospheric ingredients such as water, methane, and carbon dioxide, and also how heat flows from the planet day side to its night side. With greater knowledge of the composition of exoplanet atmospheres, and their dynamics, astronomers hope to figure out which formation theories can explain the diversity of planet types revealed over the past 2 decades. The 6.5-meter JWST will be able to scrutinize exoplanet atmospheres in more detail, but its many other roles could limit it to studying fewer than 75 exoplanets. FINESS will have the luxury of analyzing up to 1,000 planets, albeit with a smaller 75-centimeter telescope. Is our solar system's formation scenario exceptional or typical? Asks Principal Investigator Mark Swain of NASA's Jet Propulsion Laboratory in Pasadena. Some questions can only be answered by statistical samples. We need hundreds of planets,